Thunderstorms are violent. Lightning is unpredictable. Getting close enough to make measurements is virtually impossible. Scientists can't get to the lightning, so at the University of Florida's International Center for Lightning Research, they bring the lightning to the scientists.
What we did is that we used rocket-triggered lightning. You can tell lightning where and when to strike.
Dwyer and the team fire a rocket into a charged storm cloud.
Ready to fire. Arming rocket. 5, 4, 3, 2, 1, fire.
It trails a copper wire that acts like a lightning conductor. Millions of volts of electricity race from the cloud to the ground. Dwyer uses data from this to investigate how lightning can pass through miles of air. And he looks for the answer in outer space. In a galaxy far away, a star explodes. Millions of microscopic electrically charged particles are forced out into space. These are cosmic rays. Traveling at nearly the speed of light, they race across millions of miles, millions of light years to reach Earth. Dwyer wonders, could cosmic rays explain how electricity travels through miles of air? Billions of these rays bombard our planet every second. They're invisible and inaudible. But when a cosmic ray travels through the atmosphere, it momentarily rips apart the air's molecular structure. This produces X-rays, electromagnetic waves of radiation, which can be measured. Could cosmic rays be the missing link in the story of a lightning bolt? It sounds like science fiction. Even the optimistic Dwyer thinks it's a long shot.
When we got our first triggered lightning and made our first X-ray measurements, I didn't even get around to looking at the data for a couple weeks, because I wasn't really expecting to see anything. When I sat down finally, there on the screen was an X-ray pulse right when the lightning occurred. I thought, well, what's the chance of that happening? I mean, right there at the same time. So we looked at the next stroke, and there was another pulse, even bigger. We looked at the next stroke, another pulse, and another pulse with the next stroke. Every time we looked, we saw a big burst of X-rays hitting our instrument at the exact time that lightning struck.
To Dwyer, it's a clue. Something has changed the air's atomic structure, and he thinks that something could be cosmic rays.
For centuries, we've been laboring under the assumption that lightning is just a normal kind of discharge, like the finger touching the doorknob. We suddenly see now that this was wrong.
If Dwyer's right, when a cosmic ray hits a cloud, it causes a huge momentary surge in electricity, enough to create a spark, but too brief to be measured. The ray hurtles on toward the ground. The super-fast moving particles collide with air molecules and rip them apart. For a fraction of a second, the air becomes electrically conductive and provides a path down which the current can run. Now, lightning can strike. A channel of negative electrical charge shoots from the bottom of a cloud. It heads toward the ground in rapid steps. Each takes just 50 millionths of a second. As it gets closer, it has a strange effect on the ground below. Positive particles in the ground or in objects on it are drawn up toward their negative counterparts. A storm cloud can create dozens of these negative and positive channels. Most don't connect. But when they do, millions of volts of electricity race between the cloud and the ground. Lightning travels up as well as down. The air lights up. We see lightning strike, hear the air explode. In the following thousandths of a second, any remaining charge in the cloud surges up and down the channel. The bolt may appear to flicker. Lightning really does strike more than once. And all this happens up to 8 million times every day, 100 times a second.